Three.
Thank you all for coming. Our speaker today is Dr. Jonathan Kish, also known as Kish. He has a PhD from the mathematics department just down the way. He worked with an algebraic number theorist, and I got to know Jonathan because he was teaching wonderful courses in the Department of Applied Math. And then an opportunity came for me, of course, not about you, but for me, to learn more about the mathematics of cryptosystems. We looked around and guess what? Dr. Jonathan Kish knows about the mathematics of cryptosystems. And so today he's going to give us an introduction, and I hope it's fun and engaging. So thank you all for coming, and let's welcome Dr. Kish.
Thank you. Yeah, I guess I know some of you in here, but luckily I get to use my jokes again, but sorry if you've heard them before. But yes, people call me Kish mostly, and that's fine. So if I see you around, that's fine with me. My mom insists on calling me Dr. Kish. And it's like, my name is Jonathan, you named me, call me that, but she's proud, I guess, you know, that's fine. So anyway, I thought this would be just a fun, informal introduction to some of the things that I think about, and what you can do with some of the things that people like me think about. And Jim, hey, how you doing? Nice to see you. Jim and I had a conversation about computational or applied number theory, and why don't we have any courses like that? And why don't we try to design one and get it off the ground and see what happens, so that, well, we'll talk about the goals as we go forward and see what you can do with this kind of stuff. But anyway, I thought I'd just throw some headlines that I saw recently, and actually this happened the first day of this semester, the first day of our Cryptosystems class. I saw this headline, astonishing 773 million records exposed in monster data breach, right? There's more, Marriott hack hits 500 million Starwood guests. These are all just in the last couple of months. There's no shortage of these. I mean, you can just Google it. A couple of more interesting ones. You should look at that picture closely. Hot tub hack reveals washed up security protection. And in the article, they talk about how thousands of hot tubs can be hacked and controlled remotely because of a hole in their online security. And you can actually like control the temperature and the lights and the pumps and all that stuff with a smartphone or a laptop if you know what you're doing. I found that curious. By the way, I can't resist, but I don't know if you've seen that episode of American Dad, but it reminds me of that one. If you haven't, I highly recommend it. It gets worse. So here's another one where in the name of the product is the word safe, and it's a little smartwatch that your kid wears, and then you know where your kid is at all times. Well, guess what? So do a lot of other people, and this was one of the easiest hacks that they ever had, and basically there was no security built into these smartwatches, and you could follow a kid in real time. That's not good. That's just a terrible situation, obviously. So Amazon and eBay have stopped selling them, but you can see the advice that the BBC has given to parents: stop using these watches. Right? So here's a couple more headlines. Some of you are aware of this stuff, of course, but cybercrime damages to be $6 trillion by 2021, one of the biggest challenges that humanity will face in the next 2 decades. Cybersecurity jobs, there's a deficit of 3.5 million unfilled jobs by 2021, and the cybercrime epidemic is expected to triple the number of open positions in the next decade or so, next 5 years. So it does get better though. There's some good news. I saw this article in amongst my clicking. You don't need to be a hacker to get a high-paying cybersecurity job, according to this CNBC article. And in this article, you don't have to read all this subtext or whatever, but they talk about puzzle-solving ability, leadership skills, communication and business acumen being skills that you can exploit to get a good job in the cybersecurity field. And there's a professor of electrical and computer engineering at Carnegie Mellon who was interviewed in the article, and he said, I think we have perpetuated this myth that cybersecurity is based on this hacker stuff, sitting in a basement and only working on technical things. In fact, It's those with an analytical mindset that can do very well in the cybersecurity field. So you may have one more headline for you. You may have seen this one last week. Apple is compensating the kid who figured out its sketchy eavesdropping FaceTime bug. Were you aware of this one? 14 years old, figures out this bug in FaceTime. The mom frantically is trying to contact Apple and tell them about it. Apparently, Apple is, the money is private, right, the compensation. But at the bare minimum, Apple is donating to help his education in the future, which is awesome. I also read online people were trying to like figure out what kind of a compensation package they were going to give. People were like, well, maybe 5 figures would be something that you could expect if you did something like this, which is pretty awesome. Now, of course, the more computer science we all have, the better, right? I think that's taken as an axiom. The more education, the better, of course, right? Now, I'm biased, though, so the more math, the better, I think. So with this analytical mindset quote from the previous slide, I thought I'd play an analogy because it's fun and ridiculous. Not everybody who goes to the gym wants to be a professional bodybuilder, right? But it might just make you a better tennis player, or golfer, or all-around athlete, or it might just make you feel good, right? Similarly, not everybody who takes a math class aspires to be a professional mathematician, right? But it might just make you a better scientist, or engineer, or any kind of professional, and especially a cybersecurity professional. By the way, it might just make you feel good. That's one of the reasons I do it. You get a rush of blood to the head when you think you understand something. Of course, then you realize you didn't, and then that all goes away. So one of the goals of this course for me was to treat a math course kind of like a gym for your brain. And even if you're not going to end up being a mathematician, maybe we can exercise this muscle up here, and we're just going to be better off for it for a bunch of different reasons. And so maybe we can take some of the math we know, calculus, linear algebra, discrete, etc., combine it with some new math that you may not have seen before that we learn along the way, number theory especially, but maybe some abstract algebra, and use it to understand and even design modern crypto systems. So I think that upon graduation, if you're exposed to that kind of a thing, it's going to give you an advantage when you hit the field, whether you're in industry or government or academia. But also, one of the points is, maybe you find yourself 10 years down the road, you got a house, you got some kids or whatever, and then you want to go to the next level in whatever job you might be. Now, are you prepared to take that next step with a relatively doable amount of effort and time, right? So maybe getting prepared to take that next step in the future, and that's a reasonable thing to expect of you and something that you can actually do. So that's one of the points of a course like this, is to provide that kind of a foundation and that introduction to some mathematics you might not have seen before. Now, luckily, that math is extremely interesting. Again, I'm biased, but it's really beautiful. It's a blend of classical mathematics, modern mathematics, of course, engineering, computer science, policy, history, all this kind of stuff. And so I thought we would maybe do some math. And I would give you a gentle and fun, hopefully, introduction to some things that you could think about, and then we'll leverage them into what good is any of this kind of thing. What do you think? Ready? Okay. So since we're short on time, we're going to start we got to dive into the deep end and start difficult. As a joke. 3, 4, 5, right? Do you see a pattern?
Pythagorean triple.
Okay, yeah, other than they're integers consecutively, but yes, that's a Pythagorean triple. How about 5, 12, 13? Right?
Pythagorean triplets. Yeah, Pythagorean triplets.
Sorry?
Pythagorean triplets.
Which one?
The Pythagorean triplets.
Yeah, right? Yes, Pythagorean triplets. And this is Pythagoras, we think, lived around that time, by the way, right? Now, can you think of any others? And I don't mean 6, 8, 10. right? Or 30, 40, 50, or 5,000, 12,000, fine. You take those two that we know and love and then multiply them by stuff, right? That's not what I mean. Can you think of any more?
25, 20, 24 and 5, I think.
What is it?
25, 24 and 5.
25, 24, 12.
25, 24, and 5, did you say?
I'm not sure the last one.
I don't know that one, right? I don't know.
15, 20, 25?
15, 20, 25?
That one already-
Well, but that would be one of the ones we already know, right? Anyway, I find this curious that they're called Pythagorean triples, but most people know 2. Anyway, right. How about 9, 40, 41? Right, you can take my word for it. That one is a Pythagorean triple. By the way, somebody told me that in a version of a talk I gave this recently. I didn't know that one until a couple of weeks ago. But what about this one? 1771, 2700, 3229. Take my word for it, that is a Pythagorean triple. What about this one?
Oh, yeah.
Right? Okay. But what about like 101? And nobody ever says that one. How about 000? Now fine, that's open to the criticism, well that's not a triangle, right? Well, it's a degenerate triangle, maybe it has area 0, right? But so, by the way, I can't resist. Again, a little bit of history, a little bit of fun. That first triple appears on an ancient Babylonian clay tablet that was dug up from about 1800 BC, which was dug up in the early 1900s in what is now southern Iraq. It's written in Babylonian sexagesimal notation, that is to say base 60. That's a sort of a modified base 60, but that's okay. And that tablet has 15 such Pythagorean triples, none of which are obvious, like 3, 4, 5, right? So scholars still disagree as to how they knew what those numbers were, what significance they had. No, the ridiculous one on the previous slide was not on that tablet. I came up with that one. But all of a sudden, I mean, my brain starts to go like, wait, what? Some questions arise here. First off, how did I come up with that ridiculous Pythagorean triple of a couple slides ago? How many Pythagorean triples are there? You ever wondered? Maybe there's a finite list. Maybe there are infinitely many Pythagorean triples, and can we write down every single one of them? Then maybe last but not least, who cares? Right? Why are we talking about any of this in the first place? Well, you will find out. Think of it this way. This is an equation, x squared plus y squared plus z squared, and I want to solve that equation, but only when x, y, and z are integers, right? Okay? And let's say that they have no common factor, so that eliminates things like 6, 8, 10, or whatever, right before. So those are called primitive Pythagorean triples, by the way. And what do you think? How many Pythagorean triples are there? Finitely many? 16 maybe? 20? Or infinitely many? What do you think?
Infinite.
Countable.
Infinitely, what did someone say?
Countably infinite.
Countably infinite? That is correct. It turns out there are infinitely many Pythagorean triples, primitive Pythagorean triples, and then every other Pythagorean triple is either primitive or a multiple of a primitive one, and they definitely are countable, and you will see why. So, let's answer this question. Let's go back to x squared plus y squared equals z squared. Let's just say z isn't 0, okay? Because what if it is?
X and y both 0.
Well, x equals 0 and y equals 0 is the only corresponding solution, right? So that's 0, 0, 0. True, but not interesting. So ignore that one. Divide both sides by z squared and arrange to get this equation, okay? Now if x, y, and z are integers, x over z and y over z are rational numbers, right? So let's do a quick change of variables, if you will. Set s equal to x over z, t equal to y over z. Plug those in. Those are rational numbers. And so we are looking for rational numbers that solve this equation. Do you recognize that equation? What does it look like to you? Unit circle, maybe? So now, hit the reset button in your brain, and let's start over with new notation, right, so that it's familiar. X squared plus y squared equals 1. That's your favorite unit circle, right? Now, what I want to find is all points on that circle that have rational coordinates only. And fine, there's plenty of coordinates, points on that circle that have irrational coordinates, right? Like 1 over root 2, comma 1 over root 2, square root of 3 over 2, comma 1/2, right? Any others, right? Like those are the ones we know from basic trigonometry. Anyway, can you find all points on the circle with rational coordinates, x and y? It turns out you can. And you start by parameterizing the unit circle like this. Here's the unit circle. Take the point -1, 0 over here, and draw a line with slope t through that point, where t is an arbitrary but fixed real number. And that's the slope of that line, okay? Now, obviously, y minus 0 over x minus -1 equals t. That's your slope formula, right? And then you solve, and that's the equation of that line, okay? Now, substitute that line, the equation of that line for y, into the equation of the unit circle. You get this. Now, I'm going to skip through some of this algebra because it's easy. You can check it yourself. Foil all this stuff out. Combine the like terms in x. You get something like this. And if you stare at that long enough, you realize that's quadratic in x, right? But you know something. X plus 1 has to be a factor of that, because the line and the circle both go through the point -1, 0, right? Okay. So your favorite polynomial long division, pull the x plus 1 out and you get this. And that allows you to solve, set that other factor equal to 0, and you can solve for x to get that. And then you substitute that back into the expression for y from before, and you get that. So check that out. That's actually a parameterization of the unit circle. Maybe you haven't seen that one before. You all know a parameterization of the unit circle, of course, right? How about x equals cosine t and y equals sine t, where t goes from 0 to 2 pi? This one, t goes from -infinity to infinity, okay? I'll show you an animation in a second that I made in Mathematica that will help you visualize this. So now, you should be a little careful. That's true for any t in the real numbers, rational or otherwise. So I'll let you think about this. It takes a little moment's thought. That if you restrict t to be a rational number, you get a rational point, x comma y, on the unit circle, and vice versa. Okay, so think about that just a little bit. So let's set t to be a rational number in lowest terms, let's say, m divided by n, where m and n are integers. Plug it into those formulas that I showed you on the previous slide, do a little simplifying, and there you go. Look at that. That actually is a formula for every primitive Pythagorean triple. Because undo the multiplying, dividing by z squared on both sides that we did before, and now you can find what z is. There it is. There's a recipe for every Pythagorean triple that's primitive. Now, by the way, does it make sense, by the way? Any questions? By the way, I used n equals that and m equals that for no reason to find that ridiculous Pythagorean triple from before. And can you eyeball which m and n the Pythagorean triple from the Babylonian tablet would correspond to? Of course not, I can't either. So I just used Mathematica. M is 27 and n is 50, generates that Pythagorean triple that was known to the Babylonians in 1800 BC for some reason, right? And what's the point of all of this? Well, it's neat, I think, but we've been given a curve in the xy plane, and we have found, we've completely understood the collection of points on that curve where the coordinates of those points are rational numbers only. Now, let me show you that animation. Why not? Here's some Mathematica for you. And this is the first thing I'll show you. Your favorite unit circle. There is the point -1, 0 there. And you can see right there, there's a second point. And that line almost looks vertical, right? So that would be a slope that's large but negative. And then as you change t, watch this, that point's going to move. And then boom, that happens. You can tell this parameterization does not have uniform speed, obviously. But this is a way to parameterize the unit circle with those formulas that I showed you before. So now, welcome to the world of algebraic geometry and number theory, okay? Carl Friedrich Gauss, of course, all roads lead back to Gauss in this field. Mathematics is the queen of the sciences and number theory is the queen of mathematics, according to Gauss. By the way, if you've seen this before, you might be familiar with the integers adjoin I, which is your favorite square root of -1, the complex unit. You can prove that fact about Pythagorean triples using the ring of Gaussian integers is what they're called. I'll let you think about that sometime. And speaking of number theory, I can't help but show you this quote. This is the famous mathematician Hardy. Science works for evil as well as good, and particularly, of course, in time of war. And both Gauss and lesser mathematicians may be justified in rejoicing that there is one science at any rate, and that their own, whose very remoteness from ordinary activities should keep it gentle and clean. Well, sorry, Hardy, but you know, I get it. I am a lesser mathematician compared to Gauss. I'll accept that. But Hardy was a number theorist, and a very famous number theorist at that, and he thought his discipline was never going to be sullied by being applied to anything, right? Couldn't have been more wrong. Because, as you will see, as we will talk about, and that's the point of this Mathematics of Cryptosystems course, number theory provides the theoretical foundation for cryptography. Sorry, and I can't help myself. Speaking of Hardy, you can't say Hardy without Ramanujan. When asked in an interview what Hardy's greatest contribution to the field of mathematics was, he said, Ramanujan. Ramanujan was grew up poor in India with no formal education, self-taught, and wrote letters with advanced theorems and formulas and that kind of thing to mathematicians around the world. Hardy saw these letters and thought, what is going on here? Let's get him to come. And arranged for a stipend and travel expenses to come to Cambridge, and they collaborated. Hardy says that he mentored Ramanujan in the early 1900s at Cambridge. They certainly collaborated, and the world thankfully got an opportunity to pick Ramanujan's brain. And apparently numbers were personal friends of Ramanujan. Have you seen that movie, The Man Who Knew Infinity? I guess that's recent. I haven't seen the movie, but this is a true anecdote. Ramanujan had health problems throughout his life, and Hardy was visiting him in the hospital at one point. And Hardy drove to the hospital in taxi cab number 1729.
Oh no.
Do you know this story?
Yeah.
So Hardy says, oh, 1729, that's a unremarkable, boring number, right? And said, I hope that's not a bad omen. And to which Ramanujan apparently replies, oh no, it's a very interesting number. It's the first number, the smallest number that's expressible as the sum of two cubes in two different ways. What does that mean? In fact, 1729 is 1 cubed plus 12 cubed, but also 9 cubed plus 10 cubed, and that's the smallest positive integer for which that's true. Huh? Right? So I think that's more than knowing numbers as personal friends, right? Anyway, that's astonishing. Sadly, Ramanujan died in 1920 at age 32, left in a gigantic legacy. Some of you know me, I like to say that I think the word genius is overused in our society, but there's no question that Ramanujan was a genius. In particular, he was self-taught, mostly until he got to Cambridge. Now, again, by the way, another tangent, as it were. I can't help but up the ante just a little bit. There's a related equation, x cubed plus y cubed equals z cubed, right? Let's study that equation in integers, because we're talking about number theory. And notice the condition x times y times z not being 0. That just means that none of x, y, or z is 0, because that's boring. How many integer solutions are there to that equation? And as a matter of fact, let's up the ante again and say, let's just let that exponent be any positive integer n greater than or equal to 3. And how many integer solutions are there to that equation? Anyone know? There are none. So this is the subject of Fermat's last theorem, which Andrew Wiles, with help from some other people in a very significant way, finally proved in 1995 after 358 years of effort. Now, sorry, Jim, I get to tell this joke again. I used this slide and never fixed it, but that implies that he worked on it for 358 years, doesn't it? The way that it's stated. Anyway. So, speaking of Fermat, let's change the curve, but keep the question the same. Here's another curve. It's not the unit circle anymore, but how about y squared minus x cubed equals -2? You might notice there are 2 points on there with integer coordinates, 3 and plus or minus 5, which I've indicated for you there. You just plug them in to check it, right? Well, this is what's called Bachet's equation, if you just put the right-hand side equal to any integer that you want. And I want to repeat the same questions. Are there any other integer solutions to that equation? If so, how many? Can you write down a list of them? And then maybe you relax that condition just a little bit and say, how many rational solutions are there to this equation? So are there points x comma y which have rational coordinates that are on this curve, right? Well, it can be proved that if there's a rational point on this curve, and c is not 1 or -432 for some reason that we don't have time to get into right now, there are in fact infinitely many rational points on this curve. Moreover, they can be generated by the following duplication formula. And let me show you another animation that I made for you. There's your curve. This is zoomed out, so it is in fact the same curve. And there is the point 3, 5 right there, okay? And I'm going to, don't worry about the details right now, I'll zoom in a little and let you look at it again, but watch this. Well, kind of hard to see. Oh, okay. Okay. And some of you have been in my class before, you know that I like animations like this, and so it's like, well, screw it, let's just drag this slider and see what happens. Do you see what's going on? I'm generating new points on this curve, and there's all these red lines dancing around for some reason, right? That's 100 different points on this curve. Now, let's zoom in a little more closely, and maybe you can tell what's going on. So that's the same curve, the same initial starting point. Let's do one step in this process. There's my second point right there. Okay? You want to take a guess what's going on? What about there? Well, let's come back in a couple steps. Okay, there, you still can't see it. There's another one. A couple of good ones are coming up, okay? Ready, watch. Oh, you see it? How did I go from that point to that new point? What do you think?
Slope.
Slope of what?
Curve at that point.
Yeah, otherwise known as the tangent line. So those red line segments are actually on the tangent line at that curve. And it turns out that that tangent line will intersect the curve again in a point that has rational coordinates. You can think about that. It's not that hard to prove that that's going to happen. And by the way, these are they. If you start with 3, 5, you can read some of these, right? 129 over 100, 383 over 1,000, right? And then the next point is this, and the next point is that, and this is getting ridiculous, right? However, if you just ask for a decimal, you can see that some of these they're not large, right? But the numerators and denominators look complicated. So there's this duplication formula here where you can start with a rational point, take a tangent line, and find more rational points on this curve. Now, there is Bachet, for what it's worth. And speaking of Fermat's last theorem. By the way, you'll learn Fermat's little theorem in the mathematics of cryptosystems. In the 1650s, Fermat challenged the English mathematical community to show that 3, plus or minus 5 are the only points on that curve with integer coordinates. No one was able to do so. Euler thought he had a proof in the 1730s but was wrong. And it took until 1880 to prove that that is in fact a true statement. There are only 2 points on that curve with integer coordinates. By the way, in 1908, Alex Thuet, I think that's how you pronounce that, I'm not sure, proved a vast generalization of this. For any non-zero integer c, Bachet's equation can have only finitely many solutions in integers x and y. So amongst the perhaps infinitely many rational points on that curve, there's only finitely many that have integer points. Where would you start, right, trying to prove this kind of stuff? So here we come to one of the main focuses of the talk and the course, actually. Bachet's equation is an example of what's called an elliptic curve. And an elliptic curve can basically be given in this form. And no, by the way, the graph isn't an ellipse. You remember from Calc 1 or 2 or whatever that an ellipse comes from quadratic equations, right, where there are squares, but this guy's got a cubic term in it, right? There's an x cubed. The reason that it's called an elliptic curve I won't bore you with right now. You can learn about that in the Cryptosystems course or just Google it. It turns out there's a couple of different kinds of elliptic curves. Don't worry about the details, but every non-singular elliptic curve has only finitely many integer points on it. Moreover, if you look at the collection of rational points on an elliptic curve, they have a similar duplication formula like I showed you with tangent lines and points on it and that kind of thing. So, as a matter of fact, it gets even better. The collection of all points on an elliptic curve that have rational coordinates has a very specific mathematical structure. And some of you, all of you have certainly seen a vector space before, some of you maybe seen a group before. So it's what's called a finitely generated abelian group. You will learn what those terms are in the Mathematics of Cryptosystems course, don't worry about that. But it turns out that that structure, the humble question, what are these rational points on these curves, right? Starting with Pythagorean triples, if you will. It turns out that that structure can be used in cryptography. And the many applications of cryptography are pretty obvious in this day and age, right? Secure telecommunications, espionage, now blockchain technology, cryptocurrencies, that kind of thing. You can use elliptic curves for a couple of different things. Not only can you test the strength of other cryptographic protocols like RSA using what's called Lenstra's elliptic curve factorization algorithm, but from scratch you can actually design a cryptographic protocol using the rational points on an elliptic curve. Now, I find that absolutely fascinating, that's actually possible, and here we are, again, sorry Hardy, but you were wrong. So this is one of the reasons that you would actually care about something like this, and you can see that there's some calculus involved, right, tangent lines and so on. But it turns out that one of the other things you have to talk about in a course like this, and it's one of the things you have to talk about if you're a number theorist because it's awesome, is primes. And I got bit by the number theory bug and haven't turned back. You might remember this from, I don't know when you first learned this, 3rd, 4th grade, something like that. An integer is called prime, and we're going to do positive stuff anyway, or only, excuse me, if its only divisors are 1 and p, right? An integer that isn't prime is called composite, and some examples are 2, 7, 13, 19, 43, and so on, right? You can come up with your favorite prime. 2 is the oddest prime, people like to say. It's the only one that's even, right? Get it? Anyway, 4, 15, 27, 51, 100, and so on. Those are examples of composite numbers, right? Because they have non-trivial factors. Now, there are some natural questions that you might ask, or at least if you're in a number theory course, you might ask them. Never underestimate a counting problem, right? Ask how many. So how many primes are there anyway? because there are certainly infinitely many positive integers, 1, 2, 3, 4, 5, 6. You can just keep adding 1, and that's an infinite collection, countably infinite, collection of numbers, right? And in there, some of them are prime. Not always, of course. Which ones? Well, turns out there are infinitely many prime numbers. There's not a largest prime. I'm not going to prove it for you. Some of you might know how. I encourage you to think about it or look it up. There's a very, very famous proof of Euclid, as it turns out, from, I mean, it was certainly known to the Euclideans, maybe before that. About 2,300 years ago, our species knew how to prove this. So, it turns out that we have now what are called primality tests. So we're not that bad at determining if I hand you a positive integer, can you tell me if it's prime or not? Or maybe if you relax the condition, can you tell me with a certain probability if it's prime or not? We're not that bad at stuff like that. But we are much less good at factoring integers. For example, you might have noticed on a previous slide, 2021 is 43 times 47, right? It's the product of two primes, which is not a ridiculous thing to study because that's involved in RSA. So now, we exploit this fact when we try to encrypt things, that we are not good at factoring. We exploit a lot of other things on elliptic curves and in what are called finite fields, but I'll talk about that in a second. And by the way, people like cute questions that involve the year, and luckily it's odd, right? So if it was last year, obviously it's not prime because it's even, right? But what about 2019? I don't know, I like this kind of thing. Is it prime or not?
No.
Yes or no?
No. Yes. No. Divisible by 3.
Why is it divisible by 3?
Addition. You add all the numbers.
Yeah, right. You add the digits, right? 2 plus 1 plus 9 is 12, which is divisible by 3. Therefore, the original number is divisible by 3, right? But you're getting to know me. You probably are, anticipating this question. Do you know how to prove that? Like, why does that divisibility test work, right? Well, you just add them up, and if that's divisible by 3, then the original number is divisible by 3. Why? Right? Does anyone know the divisibility test for divisibility by 11? Sorry? I think it's the alternating sum of the digits, right? That's what you said? Yeah, right? So you take like the alternating sum of the digits, and if that's divisible by 11, for some reason the original number is divisible by 11, right? Okay. You can think about that. Oh, by the way, that's the prime factorization of 2019. 673 is prime. How do you know? That's sufficiently large that you can't eyeball that. How would you test if a number like that is prime?
Write a program.
Brute force, right? Talk us through it.
You try and figure out like what the square root of that is probably, and then plus 1, so you get an integer, and then you test every number under that if it divides into that.
Okay, so he's gone right to an advanced level, the square root. You might think about that sometime, but why do you have to test up to the square root of that number only? But why don't you try dividing by 2? If it's divisible by 2, it's not prime and you stop. Well, it's not even, right? Then try 3, right? If it is divisible by 3, it's not prime, stop. If it's not divisible by 3, well, you don't know, right? And then you keep dividing by the primes up to the square root of 673. If you find one that divides in, it's composite. If you don't, you can stop. And now you see the circular nature of this, because what do you got to know? What the primes are up to the square root of 673, right? So in order to test if something's prime, you got to know some primes. Anyway, I guess this is my public service announcement of the day. Isn't this neat? Like, you can talk to kids about this kind of stuff and like give them a little computer or something and be like, hey, write an algorithm, right? Like brute force. It's not that hard. And then you can see that that algorithm just, well, it's awful. Right? It's slow and terrible. So then you might be wondering, how can I make that algorithm more efficient? And then if you want to, you can spend the rest of your life working on that. And this is the area called primality tests, which are interesting in their own right, but are fundamental in cryptographic protocols. So, I can't help myself, I'm sorry. I'm a number theorist by trade anyway. Where are the primes is another question you might ask. In the collection of positive integers, where are they? Meaning, what's their distribution? That's hard. That's a question I encourage you to look into. It's called the prime number theorem. Google it sometime. But you might have to take a few classes in order to understand that one. But one thing you can prove with less effort, which I find very curious, is if you take the sum of the reciprocals of all the primes, form a series, right? And we can say it's an infinite series because there are in fact infinitely many primes. That series diverges, which is kind of neat because there are fewer primes than there are integers, right? And remember, the harmonic series diverges, but the sum of the squares converges. So it's telling you something that there's sufficiently many of them that the sum of the reciprocals diverges, right? Anyway, how about this one? 2 to the 127 minus 1. Is that prime? Think so? It is actually, thanks to Lukács, I think is how you say that. That's about 1876. He worked on this for 19 years, apparently, developing a primality test, okay? Because this is a number of a certain form. A power of 2 minus 1. It's called a Mersenne number. And if that number happens to be prime, you can call it a Mersenne prime. And unfortunately, they're not all prime, right? You can find one really easily. 2 to the 4th minus 1, that's 15, that's not prime, right? So, oh, there's Mersenne, by the way. Anyone know what the GIMPs is? Yeah, what is it?
Searching for those.
Yeah, the great internet Mersenne Prime search, right? A distributed computing project. So you can like download something that your computer will work in the background when you're not using it and try to search for these things. So now, by the way, in this one, 127 is prime, right? So maybe you got to plug in a prime to that exponent in order to get a prime. Sadly, that doesn't work either, because 2 to the 11th minus 1 is 2047. That's not prime. That's its prime factorization, by the way. So then, 2 to the n minus 1 is not necessarily prime, even if n is prime. But sometimes it is. So again, the search for a pattern, right? Can you say something about these numbers? Maybe we should try a Mersenne prime itself and plug that back in, and maybe there's some weird feedback mechanism that keeps producing primes. Well, sadly, 2 to the 13 minus 1 is 8,191, that's prime. But if you then take that Mersenne prime and plug it back into the exponent, you get that. And that number is not prime. So it's divisible by that, which it's prime. I know you're getting sick of me saying this. You can take my word for it. Anyway, again, a natural question arises. How many Mersenne primes are there? Are there infinitely many, or is there a biggest one? Right? Takers? Infinite? Guess what? No one knows. So that's an open question, actually. Which I find, just got goosebumps again, but like, I find that astonishing. We don't know if there are infinitely many primes of that very basic form, right? A power of 2 minus 1. So, maybe a better question is, who cares, right? I mean, I can talk about this on and on and on. Why would you care about anything that has to do with primes or Pythagorean triples or rational points or anything like that? Well, prime numbers play a huge role in the cryptographic system called RSA, right? And not only that, but they're essential in understanding what are called finite fields. And I don't mean something like an electromagnetic field. It's a specific mathematical object, like a vector space or like a finitely generated abelian group like I mentioned before. But a finite field is a specific mathematical object that you can study without that much effort, actually. You can go back to the Euclideans, use the greatest common divisor, use some pretty basic stuff. We've already done that in the Cryptosystems course. We've studied what's a finite field. And then you can look at the set of points on an elliptic curve over a finite field. Now you might be noticing I've put a Q there, right, as the subscript. It turns out there are finite fields for prime power order as well, not just a prime. So that could be like p to the 13th or something like that. Anyway, oh, you've seen fields before. The real numbers, the rational numbers, the complex numbers, those are examples of fields, but they're infinite, okay? So anyway, prime numbers I'm hoping to have convinced you are fascinating, they're mysterious, they're fun. You can do all kinds of stuff with them. There are open research questions, which I've just told you about, right? And you can download the software and look for the latest, largest Mersenne Prime. I think the last one I saw, if you printed it on like a little piece of tape in 10-point font, would reach from campus to Denver. It's just this staggeringly large number, way bigger than the one that I just showed you on the previous couple of slides. Anyway, knowing that you can find large primes, knowing that there are infinitely many, ends up being critically important to data security, secure telecommunications, and that kind of thing, at least to now. So right now, by the way, I thank you for coming to this talk, because if I had it my way, I would have gone to the other one. Kristen Lauder is apparently speaking right now in a different room in this building about post-quantum cryptography and what can be done. So this is just the tip, obviously, of a gigantic iceberg. Not only could you go into the theoretical side and study number theory for the rest of your life, but you can also take these ideas and run with them and start to study cryptography. And that's the point of this Mathematics of Cryptosystems course, to actually have a working knowledge of these systems when you leave CU and when you leave a course like this. So, study more math, I guess, is my, last statement for you, but again, I'm biased. Anyway, do you have any questions?
So let's thank our speaker, please. Questions, comments, assertions, philosophical entreaties?
Yeah?
X for this class?
No, actually, I mean,
Are there, what was the question?
prereqs to the class. You should know your calculus, of course. I think diffie-Q and linear algebra, like the applied math course, and then maybe some matrix methods would be great. But even if you don't have matrix methods, I think you can definitely handle it. And the more coding you know, the better. But I mean, right now we're trying to like, you know, there are some people that want to think about the cool math research problems and like how would you prove it and make a presentation about that. We had somebody last week trying to find the generators in a finite field, and so they're writing code to do that. I think it's pretty basic, actually. And the number theory that you're going to need for a course like this, we develop on the fly, because you might not have seen that stuff before, you know. And so trying to fill that niche, I guess, is part of the point. Yeah. Anything else?
How often are you going to offer? Every semester?
I don't know. I think it's going to depend. We're hoping to run it in the fall again, maybe. It's going to depend. Yeah. But to be a counter, to be a complementary course to an introduction to cybersecurity or something like that, but to actually dive into some more of the mathematical details. Yeah. Yeah.
In industry, this seems magic to a lot of people because it's kind of the intersection of mathematics, computation, and then engineering as it plays out. Can you comment on that as a mathematician?
Well, yeah, my background is in pure math, obviously. And I now teach for the applied math department for reasons I won't bore you with, but I think I've changed. And I used to be pretty die-hard or hardcore. The theory is, what's important, and the why is what's important, and frankly, screw everything else. But I've changed, and I think that teaching for the applied math department, being surrounded by people, and then asking interesting questions, I've completely changed my attitude. And I think that there are just as many cool questions in industry that use stuff like this, as there are just like, what's a finite field and what's the group of points on an elliptic curve. I think that a good blend of the two is incredibly important. And the more math that you can possibly leave CU with, for example, the better. And I know people in industry that, frankly, I had someone at some cocktail party was like, what's an elliptic curve? I was like, oh boy. It's kind of a big question. And I'm worried that starting at that point and being super busy and having a life to deal with, it might be too big of an ask, honestly, to like learn all that stuff. But trying to find a balance is one of the goals of the course. can we get in one semester to like, what's elliptic curve cryptography for the working engineer, for example? And to be determined, I guess. Yeah, I think that it's fascinating. I think that's what Kristen Lauder's talking about because she works at Microsoft. And I think it couldn't be more important and more interesting and a way to get people interested in both. Do you know what I mean? Like, I think I was late to realizing that the applications are awesome. Yeah, I don't know if I addressed your question.
It's very hard to engender the passion for the beauty of mathematics and engineers, but I think you can kind of meet in the middle beyond that.
Yeah.
It's kind of a cool way to intersect between the two.
Right, yeah, definitely. And I mean, not everybody needs to know why these theorems are true, you know, like the finitely generated abelian group thing, but at least what is that thing, what are some examples, and what would you do with it? And then you can leave the proofs of some of those are hard. That takes time. But you can leave the proofs to the mathematicians, thankfully, right? Yeah.
Just thinking when you were talking about the watch for your kids that they found was not a good product to buy. Like the FDA puts a label on a product and we have some assurance that it's safe to use. Have you heard of there's any discussion of there being like an equivalence to that role for future products? Like, hey, before I sold you this thing, I handed it over to these guys and they put a stamp on it.
Right. To be honest with you, I don't know. Now, I'm not an expert in that stuff, like the Internet of Things, you know, I mean, it's kind of frightening, frankly, when you think about it. I am not an expert in that area. I think that's a great question. Does anyone know? Because I certainly hope there is.
Dan, did you want to say something? That's a fascinating, yeah, let me put a little bit on that one, but so the whole Internet of Things is a tremendously interesting topic. It applies a lot to what Jonathan's talking about here, because we need to do crypto we need to do a lot of mathematics in a slightly different way. I have a different amount of resources that I put on my thermostat or worse yet, my embedded device than I do on my laptop. So there's a whole interesting step there, and that's where Jonathan, Jim, myself, and the CU program as a whole, we think one of the areas that we're going to focus on for cybersecurity at CU is cybersecurity with the Internet of Things. Circling back to one of the questions that was asked earlier about the courses, we're hoping to run the course, ideally every semester. We have the demand, and I think if we get the word out, we will have that demand. For the folks of you who are here, this is an exciting topic, and and there's a ton of interesting stuff. Whether you're on the more purely applied side to say, all right, how do I make my Nest thermostat secure? To more of the what's the underlying algorithm behind this? Mm-hmm. We're hoping to cover the whole scope on that, and we're hoping to throw Jonathan into more and more. So hopefully we'll see more. That's not a really good answer to that question, but that's kind of my generic.
Well, you know, I didn't even say anything about like, hey, how efficiently do these algorithms run? I mean, that's a whole other question that we're going to dive into, and it's fascinating, and that's part of the modern perspective on the mathematics, because you might have the Euclidean algorithm, for example, to find the GCD, but we didn't think about like how quickly can you run this thing until relatively recently. So I think that's another, speaking of, you know, the connections to industry and so on, and that's one of the things I've learned, like, oh, this is fascinating, and like there's a lot of smart people doing cool stuff with that.
And I guess a comment on that, the people that can actually inform, so RSA, Bitcoin and encryption, kind of elliptical curve, there's a set of assumptions that people are operating on, but most of them are not kind of first order practitioners and whether they're true or not. And so this is kind of where it's your suggestion of an FDA for cryptography, mathematicians could theoretically play that. Mm-hmm. I don't know that they necessarily get organized in doing that I've seen.
Well, and right, you might have caught that in a slide before. It's like, well, we're terrible at factoring things and we exploit that to encrypt. It's like, well, we're terrible now, but who knows what's going to happen? And, you know, again, in the post-quantum world, for example, or with the, you know, elliptic curve discrete logarithm problem, for example, we haven't thought of it yet, but I don't know. I don't know. Like, what's on the horizon, what is somebody thinking of, and who knows when some awesome, interesting, wacky idea out there is going to be a completely different perspective on this.
So a thing that is happening is that the National Institutes of Standards and Technology in Gaithersburg, they have a group, a mathematics and computer science group, that actually thinks about these kinds of issues to want to certify that these numbers are exactly unbreakable given sort of modern technology. They try to do things like that. And so there are standards that are always evolving, et cetera. And as Jonathan said, can't predict the future, but there are some folks who are thinking about those things.
And those folks are coming and talking to us. We're trying to get as many as we can to come give guest lectures in the crypto class as well. Yeah.
One last kind of loaded question. So where do you see quantum computing going in the future, and how does that?
Well, you know, I guess I'll be completely honest with you, and I guess that's a quote from Al Pacino, but tell the truth, it's the easiest thing to remember. I'm not an expert in quantum anything, honestly, and I do know that I've read anyway, that there are some algorithms out there that can basically factor large integers, and it irritates me that that's true and I don't understand it, and so that's part of my free time life, is really trying to get up to speed on that kind of a thing. And so, you know, frankly, I wish I could have gone and seen Kristen Lauder talk about this. She certainly could have answered that, I'm sure. But there are things that, I'll say this, and I do know about this, there are things that we think are robust, at least to the quantum attacks that we can put, that we know about now. But honestly, that's as far as my knowledge goes.
And I think that's the best answer, honestly, that anybody can say. I don't think there is a definitive answer. Like, oh, yes, someday we're going to have, we don't know. But it does, the most interesting thing on that I've encountered is thinking about this makes you think about the mathematics a little bit differently. So if you could do factor factorization, how does that change? So I think the interesting part for the students is less about, you know, will we have giant quantum computers in the future or not? But how does that, you know, as you go through this, how does that make you think? How does it make you think differently about? Oh, wait a minute. Okay, so suppose factorization is actually a real thing to do. That doesn't mean everything is easy. It doesn't throw everything away.
Right.
But it does make you think about it in a slightly different direction.
Right.
There's a lot of really exciting potential stuff for all the students.
I think we have a student, at least one, or maybe a small group of students that are going to do a project on quantum cryptography in our course. We have a professor in the physics department I hope is going to come and give a guest talk in our class and talk about it. So yeah, lots and lots to learn and lots to do, and I think it's all just, we're trying to stay as close to the edge as we can. As Jim likes to say, it's moving exponentially, so we're trying to constantly, you know, adjust and see over that edge, but that's one of the goals, yeah.
So any other questions, comments, assertions? Again, let's thank our speaker.
Thank you.
Thank you all for coming. Students of the course, you know what you have to do. There's an essay, et cetera, et cetera.